Good evening, everyone. I'm Manish Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bangalore. Welcome to this week's live interaction for the NPTEL course Engineering Mathematics 2. This course has a code NOC 23MA25. This week we'll be covering some content related to the concepts taught in week 9, which primarily include Fourier integral transform, Fourier cosine and sine transforms, their different properties such as linearities and uh, Parseval identities, transformation and derivatives. Then what is Fourier transform and how do we again go about taking derivatives using Fourier transform. With that in mind, as is the custom every week, we'll be going through a few problems which will try to help us elucidate these concepts. So the first problem is, let f and g be piecewise continuous and absolutely integrable function. The Fourier integral representation of the function 2f plus 3g is what? Okay. So we are given that f of x and g of x are two functions and that they are absolute integrable functions, which means that the integral of f of x modulus of f of x dx over the entire real line is, it basically converges. Same is true for integral of modulus of g of x dx over the entire real line. This is an important condition because this allows us to use Fourier integral transform, which initially starts by assuming the function f of x is periodic between minus L to L, and then we extend L to infinity so that f of x can be a periodic function over the entire real line. With this condition being given and the fact that it is also piecewise continuous, we can apply Fourier integral transform. So Fourier integral transform of f is nothing but integral of infinity a of alpha cos of alpha x plus b of alpha sin of alpha x times d alpha. So this is f of x itself written in integral form. Same can be written for f of g. And before I write for I can write a of alpha and b of alpha, which are coefficients, given as 1 by pi integral minus infinity to infinity f of u cos of alpha u du, and similarly b of alpha being 1 by pi integral over the entire real line f of u sine of alpha u du. Similarly, I can write the Fourier integral transform for g to be integral. I'll write a dash of alpha cos of alpha x plus b dash of alpha sine of alpha x, all integrated with d alpha. So if we simply want to write for the function 2f plus 3g, what that would be is suppose 2f plus 3g I write as another function h. So I want to write f of h, that is nothing but h of x is equal to integral. I'll write a double dash of alpha cos of alpha x plus b double dash of alpha sine of alpha x whole times d alpha. Now the integration limits, and since alpha is any variable, it's essentially the same given over the entire limit. So we need to check if a double dash and b double dash are in any way related to a dash and a. So a double dash is nothing but 1 by pi integral h of u cos of alpha u du over the entire real line, which is nothing but 1 by pi. I'll now write h as h in its components f and g, so which is 2f of u plus g of 3g of u cos of alpha u du. Right, so we can split this sum across the integral operator to get 1 by pi integral minus infinity to infinity f of u 2f of u cos of alpha u du plus minus infinity to infinity 1 by pi minus infinity to infinity 3g of u cos of alpha u du. This, if you notice, is nothing but 2a, and this, if you notice, is nothing but 3a dash, which means we get a relation of the form a double dash is 2a plus 3a dash. Similarly, if we calculate b double dash using 1 by pi h of u sine of alpha u du, and then substitute 2f of u plus 3g of u in place of h of u, we would again get an integral which will be split between the terms of f and terms of g to again obtain us twice of the coefficient of with respect to f of u and thrice plus thrice of the coefficient with respect to g of u. So that essentially could be written as b double dash is 2b plus 3b dash. And next we can observe that f would where f would be linear in terms of its coefficient alpha and a, a of alpha and b of alpha. So for our case, f of h uh, would essentially look like which f of h, which is f of 2f plus 3g, would essentially be would have the coefficient a double dash and b double dash. So 0 to infinity a double dash of alpha cos of alpha x plus b double dash of alpha sine of alpha x d alpha. Now, if we substitute these two relations inside these bracket, I would get. I'll remove this and get some space here. So that would look like 0 to infinity 2a of alpha plus 3a dash of alpha cos of alpha x plus 2b of alpha plus 3b dash of alpha sine of alpha x. This whole term is then multiplied, integrated with respect to d alpha. If I now take out these terms together and these terms together, I essentially end up obtaining twice of f of f plus thrice of g. So this term and this term feed to f of f, and this term and this term feeds to f of g. So through this problem, so the answer is option A, and through this problem we can understand that Fourier integral representation is a is linear in terms of its arguments, which are functions f and g. Okay. If this is clear, we can now move to the second problem. The second problem states Fourier integral representation of function f is given by f of x equaling integration from 0 to infinity a of alpha cos of alpha x plus b of alpha sine of alpha x d alpha. And then we are given f of x to be equal to e raised to minus x when mod of x is less than 2 and 0 otherwise. So we are asked to find what b of alpha, what is b of alpha in the Fourier integral representation of f of x. So if you remember, how do we calculate b of alpha? It's a procedure that is analogous to calculating coefficients of the Fourier series, which is from where we conceptually derive or arrived at the Fourier integral representation. So b of alpha is nothing but integration of minus infinity to infinity f of u sine of alpha u du. We are given that f of x is 0 when mod x becomes greater than 2. So if I look at this function, it would look something like this. They'll say x equal to 2, and the same thing other way, x equals minus 2, and then it suddenly jumps and goes to 0. So across the real axis, the only portion where it is non-zero is from minus 2 to 2, x equaling minus 2 to 2, or in this case u equaling minus 2 to 2. Sine of alpha u du. So we could further say split this integral into minus 2 to 0 and another integral from 0 to 2 and substitute mod of u properly. For the negative case, mod of u will be u, and for the positive case, mod of u will be, sorry, for the negative case, minus mod of u will be u, whereas for the positive case, mod of u, minus mod of u will simply be minus u. So we could do that, or we can make a quick observation here. You can see that if I say rewrite this as g of u, right? So my g of u is e raised to minus mod of u sine of alpha u, right? And if I now write this as g and calculate now at g of minus u, so it will be minus e raised to minus mod of minus u sine of alpha times minus u. It's mod of minus u is mod of u equals mod of minus u. So we'll just substitute that, and sine of minus x equals minus sine of x. So it gives sine of alpha u into minus 1. I'll take the minus side ahead. From these two relations, what we can say is that g of u is an odd function. And if this essentially means that if we are integrating g of u over some range minus a to a, it should vanish. So in our case, this g of u, or for more formally, what this expression which precedes our differential sum is essentially called as integrand. So this thing is called as an integrand, and in our case, this integrand function turns out to be an odd function, which has the property that if it's integrated symmetrically about in an on an interval which is symmetric about the origin, then it should vanish, which basically gives us that P of alpha should go to 0. So option B. Okay, if this is clear, we will now move to the next problem. Problem number 3. Fourier integral representation of the function f is given by f of x equals integration 0 to infinity a of alpha cos of alpha x plus b of alpha sin of alpha x d alpha. And now we are given some f of x as follows. I draw it on the axis, xy axis. So what does this function state? If x is between 0 to 3, so x is between 0 to 3, y equals 4, f of x equals 4, but it doesn't, the endpoints are not included, so we'll have to be careful to not include the endpoints. And another thing that it says is x belongs to 0 minus 3 to 0. Then again, the endpoints are not included, so this should be minus 4. Just label 1, 2, 3, minus 1, minus 2, minus 3, 1, 2, 3, 4, minus 1, minus 2, minus 3, and finally minus 4. And at all other regions, so that would include the point 0, the points 3 and minus 3, as well as the rest of the real line, f of x goes to 0. Okay, and now we are asked to calculate a of alpha. So we can quickly see a few things. Firstly, that this is absolutely integrable over the entire real axis, and it is also piecewise continuous, meaning that an integral transform will exist. So of x, I'll just write down absolute integrable and piecewise continuous function. So integral transform can exist. We could have looked at in the case of previous example as well. You can see again here also that it's piecewise continuous and also absolutely integrable, meaning that the shaded area is bounded. Yes. Okay, and here is this function's shaded area, and we are asked to get a of alpha. So a of alpha is nothing but integral minus infinity to infinity f of u cos alpha u du. Again, we look at the integrand for this case. Again, say rename it as g of u. What do we see here? So my g of u is nothing but 4 cos of alpha u when u belongs from 0 to 3 and minus 4 cos of alpha u when u belongs from minus 3 to 0 and it is 0 otherwise. So g of minus u will either be, so suppose u lies between 0 to 3, so minus u will now lie between, minus u should lie between 0 to minus 3 to 0, which should make our function here minus 4 cos of minus alpha u. Similarly, if u belongs from minus 3 to 0, our function, our minus u will lie from 0 to 3, which should give our function the value 4 cos of minus alpha u. and for all other points it's again 0. So since cos is an odd function, sorry, an even function in itself, cos of minus alpha u is actually nothing but cos of alpha u. And same goes for this term as well, which basically gives us that g of minus u equals g of u minus g of u, which means that g of u is an odd function. And therefore, if you were to integrate g of u du with an interval of width 2a, which is symmetric about u equal to 0, then the integration should vanish. In our case, a of alpha turns out to be integral of minus 3 to 3 g of u du. So it should vanish, which basically again goes to option C, a of alpha equaling 0. So what these last two problems essentially help us understand that if the function f of x is such that it is either even or odd, we can utilize the simple observation that if the one of the integrands, either a of alpha cos of alpha x or b of alpha sin of alpha x, would be such, a of alpha or b of alpha would be such that they would have an odd integral, and that would mean one of those terms would cancel out, making the rest of the computations easier. So problem number 4. Here we are given again Fourier integral representation of this function, and we are asked to find, yeah, we are asked to find a of alpha for this case. So the function that we have been given is e raised to minus x when x is greater than 0. So I'll show this as 1, this as 0, x greater than 0, so 0 is not included, and this is our exponentially decreasing function. And for every other point, it's basically given as 0. Uh, a quick check of integration of e raised to minus x would show us that this whole thing, this shaded area is essentially bounded, which allows us for, like, so f of x is absolute integrable. The shaded area is finite, and f another thing is it is piecewise continuous function. So thus a Fourier integral representation of f is valid, and now we can calculate a of alpha to be 1 by pi times integral minus infinity to infinity f of u cos of alpha u du. So I'll make a use of a particular formula here for cos of alpha u. So we know that e raised to I theta is nothing but cos of theta plus I sin theta, and therefore we get that e raised to I theta plus e raised to minus I theta by 2 is cos of theta. So I'll move this pi and another 2 that we'll get from substituting this formula here to the left hand side, which should give us 2 pi a of alpha is integration of minus alpha from minus infinity to infinity e raised to minus x times e raised to I theta, sorry, e raised to I alpha u plus e raised to minus I alpha u du, which gives us 2 pi a of alpha is integral minus infinity to infinity e raised to e, e raised to I alpha into u minus x plus e raised to minus I alpha Oh, sorry, this should be f of u, not I alpha u minus u, and this will be I minus I alpha u minus u du, which is integrate from minus infinity to infinity e raised to u times I alpha minus 1 plus e raised to u times minus I alpha minus 1 du. We know that integration of e raised to ax dx is nothing but e raised to x by a with provided the appropriate limits. So my 2 pi a of alpha becomes e raised to u I alpha minus 1 upon I alpha minus 1 plus e raised to u minus I alpha minus 1 upon I alpha minus 1. And I the limits here are actually from not from, so the starting point of limits was minus infinity to infinity, but once you substitute the fact that it is 0 for negative values of we the limit converts from 0 to infinity. So the first term you can see has an e raised to minus u. When it goes to infinity, this term would vanish. Similarly, this term also has an e raised to minus u, whereas e raised to minus I alpha u would give us a couple of trigonometric terms. So when we substitute u tending to infinity for both of these terms, they'll go out to 0. And when we substitute u going to 0, this both of these terms will go to 1. E raised to u will go to this will become e raised to 0. This will also become e raised to 0. So 1. So for the infinity, it's 0 plus 0 minus 1 by I alpha minus 1 plus 1 by minus I alpha minus 1, which is 1 by 1 minus I alpha plus 1 by 1 plus I alpha. If you just multiply these two, it becomes 2 upon 1 plus alpha square. So this is 2 pi a, which means a is 1 by pi 1 by 1 plus alpha square, which is option number B. Yeah, so in this particular problem, we are able to find out Fourier integral representation, specifically one of the coefficients required for computing the Fourier integral representation. And okay, with that in mind, we now move to, and if there are no more doubts for this particular example, we then move to problem number 5, where we are asked to calculate Fourier integral representation uh, like b of alpha in the Fourier integral representation. For this case, f of x equals x square, x is less than or equal to 4. It will be difficult to plot, but it should look something like this. And after at x equal to 4 and x equal to minus 4, it should have the value 16 because it's less or equal to, and then after that it will be 0 everywhere. Again, you can see that this area is bounded, so f of f is f turns out to be absolute integrable over the entire real axis, and secondly, f is a piecewise continuous function, therefore Fourier integral representation is valid. Thereby we use the formula that we know for b of alpha equaling 1 by pi integral minus infinity to infinity f of u sine of alpha u d alpha. So for our case, uh, this is pi times b of alpha is nothing but integral minus 4 to 4 because it vanishes everywhere else. F of x vanishes everywhere on the real axis except when x belongs from minus 4 to 4. This is x square sine of, sorry, u square sine of alpha u du. Again, we can see that this is, if I write this integrand as g of u, then g of minus u is nothing but minus u square sine of alpha into minus u, which is minus u square sine of alpha u, which is minus g of u. This tells us that g of u, the integrand g of u is an odd function, meaning that this integration, if when the integration is symmetric about 0, then the integration of the odd function should vanish, which for our case means that pi times b of alpha equals 0 or b of alpha equals 0. So whenever we try to integrate, it's a good practice to check whether the integrand is odd, and if the provided function is symmetric, that would help you save a lot of computing time. A quick check will save you a lot of time. Problem number 6. Problem number 6 is a Fourier integral representation of function f is given by a of alpha cos of alpha x plus b of alpha sin of alpha x. We'll quickly have a look at how f looks. So for x equals 0 to 1, and then there's x from minus 1 to 0. When x is between 0 and 1, function is 1 minus x, so it will start at 1, but it doesn't include 0, and it will go to 0 at x equal to 1, but doesn't include the point x equaling 1. When x is between minus 1 to 1, so 1 at x equal to minus 1, 1 plus x will go to 0, and when x equals 0, 1 plus x will go to minus 1. Again, 0 is not included, so 0 follows the third rule, which is f of x equals 0 to all of the points. And okay, so this is how our function f of x would look like. Again, we can see that it is absolute integrable as well as piecewise continuous, meaning Fourier integral representation is valid. And now we calculate b of alpha. So pi times b of alpha is nothing but integral of minus infinity to infinity f of u cos f of u sine of alpha u du. Okay, can we make any remarks about this particular integrand function? So, okay, let's see. Is there anything here that we can use? It seems like this is indeed an odd function f of u. So if I were to take f of minus u, suppose u lies between 0 and 1, then f of minus u would be minus 1 times 1 plus minus of 1 plus minus u, which is minus 1 plus u, which is minus of 1 minus u. So u belonging to 0 to 1 And when u would belong from -1 to 0, f of minus u would be nothing but 1 minus minus u, which is 1 plus u, which is minus of 1 plus u. So in both the cases, f of minus u turns out to be equal to minus f of u, which would mean that f of u is an odd function. So f of u is odd. Similarly, we also know that sine of alpha u will also be odd. So the product will be an even function, which means that rather than integrating the over the uh, entire um, entire interval, we could make use of only half the interval and then double the, so which would give us pi times b of alpha is equal to twice of integral 0 to 1. Again, everyone else, it is simply vanishing out. So it is 1 minus u sine of alpha u du. So I'll just write pi by 2b to be equal to 0 to 1, 1 minus u sine of alpha u du. If I take, if I integrate this by parts and take and integrate this term initially, so it will be 1 minus u sine of alpha u, integration of sine of alpha u will be minus cos of alpha u by alpha. So this term will have the limit 0 to 1. Okay, and the other term that we would have is minus integral 0 to 1 differentiation of 1 minus u, which is minus 1, and this integrated term, which is minus cos of alpha u by alpha du. Now, once we substitute u equal to 1, we see that the first thing will cancel out, and if we substitute u equal to 0, this is 1 times minus cos of 0. So cos of 0 we know to be 1. So 1 times minus 1 upon alpha. So it's minus 1 upon alpha. No, sorry. So the first term when we substitute u equal to 1 is 0. The second term when we minus 1 upon alpha. And now we can see that there are two minuses inside. I'll just sum them up. And now we want to integrate cos of alpha u du, which is nothing but sine of alpha u by alpha square. The limits are 0 to 1. So this is 1 by alpha minus sine of alpha u, which is at u equal to 1. So sine of alpha by alpha square minus sine of alpha u when u equal to 0 is nothing but 0 alpha square. So this term should vanish. So I get pi by 2b to be equal to 1 by alpha minus sine of alpha by alpha square, which is nothing but alpha minus sine of alpha by alpha square. Therefore, I get b of alpha to be 2 times alpha minus sine of alpha upon pi times alpha square, which is option A. Okay, so here also we could have done the entire integration over twice the interval, while in this case it turned out that the integral, the function f of u was indeed an odd function, which means if we had the integral f of u sine of alpha u, that would be even, which allowed us to only look at half the interval and then double its integration value. Whereas if for this case were we interested in a of alpha, then our integrand would have looked like f of u cos of alpha u. So that's a product between an odd function and an even function, which is again an odd function. And so we wouldn't have been required to calculate A of alpha at all. We could have directly written it to be 0. If this problem is also clear, we then move to problem number 7. Now we are asked to calculate Fourier cosine in integral representation of f of x, and in that we are asked to calculate A of alpha, and we are given this particular data. So f of x is e raised to minus 3x plus e raised to minus 5x when x is greater than 0 and 0 everywhere else. To calculate Fourier cosine integral, we essentially have the coefficient A of alpha again given as minus pi to minus infinity to infinity f of u cos of alpha u du, which is nothing but, so pi times A is integral 0 to infinity e raised to minus 3x 3u cos of alpha u du plus integral 0 to infinity e raised to minus 5u cos of alpha u du. So both of these, if you think about it, they look very similar except for this particular coefficient. So suppose as a trial problem, we'll look at integrating e raised to minus au cos of alpha u du, and once we have this value, we'll just substitute a equal to 3 and a equal to 5 in our in the case of our problem. Again, I'll rewrite cos of alpha u as I've written previously to be half of e raised to I alpha u plus e raised to minus I alpha u into du, which is half of integral 0 to infinity e raised to minus u times a minus alpha I plus e raised to minus u times a plus alpha I du. So if I just integrate this, it turns out to be e raised to minus u alpha plus alpha alpha minus, sorry, a minus alpha I upon a minus alpha I minus of the whole thing minus e raised to minus u a plus alpha I upon a plus alpha I when we take the limits from 0 to infinity. So once I plug in infinity, we'll have e raised to minus of infinity times some complex constant, which should vanish. And if we take u equal to 0, then this will be e raised to minus 0. This will be e raised to 0. This will also be e raised to 0. Both are equal to 1. So if I take into account the minus signs as well, it would be half of 1 by a plus a minus I alpha plus 1 by a plus I alpha, which is half of, I'll multiply both of these. So a square plus alpha square times a plus I alpha plus a minus I alpha, which is 2a plus a upon a square plus alpha square. Now we simply substitute this in our problem. At a equal to 3, we get 3 upon 3 square plus alpha square, and at a equal to 5, we get 5 upon 5 square plus alpha square. So my a of alpha turns out to be nothing but 1 by pi times 3 upon 9 plus alpha square plus 5 upon 25 plus alpha square. So for the Fourier cosine integral, we actually take integral 2 by pi. We assume f to be, or symmetric about y-axis. So this is basically 2 by pi times 3 by 3 square plus alpha square and 5 by phi square plus alpha square. So which turns out to be option number C. So we are not calculating Fourier integral transform, but we are actually calculating Fourier cosine integral transform. So which is why the limits are wherein we only look at like similar to how we did in Fourier series, where we looked at half series expansion, sine series and cosine series, assuming f to be either even or odd. Similar thing we do here. So that allows us to only look at the integration from 0 to infinity. So this gives us option. This gives us this particular form of the integral. So we end up with option C. Hope this one is clear. Okay. We now move to problem number 8. Again, we are asked to calculate Fourier cosine integral representation, and yeah, similar thing, except now we are given f of x is sine of x, and it is bounded between 0 to pi. So my Fourier cosine integral representation would look like 2 by pi integral of 0 to infinity f of u cos of alpha u du, which is nothing but 2 by pi integral 0 to pi sine of u cos of alpha u du. I'll take the 2 inside. So this basically becomes 2 sine A sine B, which is cos of A minus B, 2 sine A cos B, which is sine of A plus B plus sine of A minus B. So my pi by 2 times A becomes integral 0 to pi. So pi times A becomes integral 0 to pi 2 sine u cos of alpha u, which is nothing but sine of u plus alpha u plus alpha u plus sine of u minus alpha u du, which is integral 0 to pi sine of so sine of u plus alpha u, I can write that as u times 1 plus alpha, and if I am taking the integration of sine of k times u, so integration of sine of k times u would be nothing but minus cos of ku by k. So for our case, both of these are of the type of sine of ku. So we get minus cos of u times 1 plus alpha upon 1 plus alpha minus cos of u times 1 minus alpha upon 1 minus alpha with the limits 0 and pi. Okay, I'll just continue this here. So I have got pi times a equaling. Since both of these terms are negative, we can actually flip this whole thing around in terms of the limits of integration. So I'll take the negative sign and flip the limits of integration from pi to 0. So if I substitute 0, I've got cos of 0, which we know to be 1, and again here is also cos of 0. So the first is 1 plus 1 by 1 plus alpha, it's 1 by 1 minus alpha, minus if we put u equal to pi, so it becomes cos of pi plus pi alpha upon 1 plus alpha plus cos of pi minus pi alpha upon 1 minus alpha. So we have to calculate this term. I'll use one of the blank sheets at the end. So I've got cos of pi times 1 plus alpha upon 1 plus alpha plus cos of pi times 1 minus alpha upon 1 minus alpha. Now for this is essentially cos of a plus b, so pi plus pi alpha, and this is cos of a minus b, so pi minus pi alpha. And I'll multiply the first term with numerator and denominators with 1 minus alpha, and multiply the second term's numerator and denominators with 1 plus alpha. So it will give me 1 minus alpha times expansion of this term. So that is cos pi alpha minus sin pi alpha. So this term is minus 1, this term is 0, plus 1 plus alpha times, again I'll expand it, so cos of pi alpha plus sin of pi alpha. Again this term is minus 1, this term is 0, and then we have this whole thing divided by 1 plus alpha into 1 minus alpha, which is 1 minus alpha square. So on one hand I've got 1 minus alpha into minus 1. So I'll write it as alpha minus 1 cos of pi alpha plus minus alpha minus 1 cos of pi alpha upon 1 minus alpha square. So plus alpha and minus alpha will cancel out to give us minus 2 times cos of pi alpha upon 1 minus alpha square. And from the first term of the integration, we had from this term we have essentially 1 minus alpha plus 1 plus alpha upon 1 minus alpha square. So it should be twice upon 1 plus alpha square minus this term, which is 2 cos of pi alpha upon 1 minus alpha square. So if we bring these two terms together, this turns out to be sorry. If we bring these two terms together, it turns out to be 2 by 1 minus alpha square times 1 plus cos of alpha pi, which gives us a equaling 2 by pi times 1 plus cos of alpha pi upon 1 minus alpha square, which is nothing but option D. So here if the minus feeds here, then we essentially end up with our form of the answer. So in this way, problem 8 also deals with Fourier cosine integral. With that out of the way, we now look at problem 9. So it is an example problem for Fourier sine integral representation. So Fourier sine integral representation, and we are given that f of x equals 1 when x is between 1 and 3. So it would be like this, and 0 elsewhere. Okay, so this is what we are given, and we are asked to calculate b of alpha. So b of alpha is nothing but 2 by pi times integral 0 to infinity f of u sine of alpha u du, which in our case is pi by 2 times b equals integral 1 to 3. Oh, it's only 1 times sine of alpha u du, which is minus cos of alpha u by alpha, substituting 193. So which is cos of alpha minus cos of 3 alpha by alpha. Therefore, we get b of alpha to be 2 by pi times cos of alpha minus cos of 3 alpha upon alpha. So, a more straightforward example, but about how do we obtain the Fourier sine integral representation. So, numerically, this was straightforward, but I hope this touches upon what has been taught for Fourier sine integral. And finally, we move to the last of the selected problems, problem number 10. We have been given that f hat of alpha is the Fourier, g of alpha is the Fourier transform of f of x, and then we are asked to calculate Fourier transform of f of minus 2x. The easiest way to do this would be using scaling property of Fourier transform, which essentially tells us that f of f of alpha x or kx is equals 1 by mod of k f of f hat of alpha by k. So in our case, f of minus 2x equals nothing but 1 by mod of minus 2 g of alpha by minus 2. So which is option number B. Yeah. So this apart from the scaling property, Fourier transform has other properties such as linearity, shifting, and duality. And it also finds some uses in the case of convolution as well as derivatives, some of which were covered for this week's content as well as in next week's content a bit. So with this in mind, I have like this set of problems for this week has been with this in mind. This particular week's set of problems has been done. If there are any doubts related to this week's content, you can ask them now. Okay, I presume there are no more doubts for this week's session. Anyways, thank you for attending this. I'll see you again next week.